So today what we are going to do is we are going to design a one-way slab with the following dimensions. These are 6 meter by 3 meter of a slab. These are the clear dimensions of the slab. The slab is being loaded by a live load, that's 3 kilonewton per meter square, and the dead load of 2 kilonewton per meter square. Now the slab is provided with supports on all the four sides, on all the four edges, and there is an M20 grade of concrete and Fe4 500 of steel. So this is there is a zero point 0.3 meter support on all four sides, the clear span being 6 meter and 3 meter. Now, in the step number one, what we are going to do is to determine the thickness of the slab. Now, how do we do that? Now, this is based on the deflection control. As per the deflection control, that's given in IS 456, and the span to depth ratios are taken, and these ratios are the length, that's clear length here, to the depth of the that's the effective depth for a simply supported condition would be 20. So this L is the shorter direction length. Now, why is it the shorter direction length? Because that would dictate the along the shorter direction, that would dictate the amount of deflection that would happen at the maximum deflection point, and that would be dictated by the shorter direction span. If even if we try to determine what the deflection depends upon, it depends upon two things. One, it depends upon the stiffness, and other, it depends upon the length. That's the span. Now, it's inversely proportional to the deflection is inversely proportional to the stiffness of the slab or of any other structural element, and it's directly proportional to the span of the slab. So there will be more deflection when there is more span of the slab. Now, and because the shorter direction is also supported, if it was not supported, then the condition would have been different. But because the shorter direction is also supported, thereby this 3 meter, which is along the shorter direction, would dictate the deflection control. So I would thereby say that because L is the clear span, that's 3. So into 1000 in mm, so I'm converting this, divided by 20 would be equal to D for if we want to get the minimum depth of the slab for the deflection control check. So that depth of the slab would be around 150 mm. There is one more conventional method to determine the thickness of the slab, and that could be done by determining the span by so that could be determined from the span to the deflection control. Thereby, if the cover of the slab is 30 mm and the bottom bar is around 12 mm in dia, this is an assumption. Now, cover is usually provided as 30 mm. So the total overall deflection would be 150 plus 12 plus 30, that's 192 mm. And the slab would be of a thickness of around 200 mm. Now, in step number two, because this is the minimum that's required, 192, and so we are providing a slab of thickness of 200 mm. In step number two, now this slab is 200 mm in thickness, and uh, in step number two, we are calculating the loads on the slab. So the total load on the slab is 3 kilonewton per meter square is the live load, 2 is the dead load, and next we need to calculate the self weight of the slab. Now the self weight of the slab would be 6 into 3 is the area into the thickness. So that would give you the overall thickness, which is 0.2 into 25 is the density of RC concrete, reinforced concrete. So that comes out to be 90. That would be 5 kilonewton per meter square. If we divide it again by 6 into 3, so you get 5 kilonewton per meter square. So the total load now is 5 plus 5 kilonewton per meter square. And if we want to calculate, this is an area load, if we want to calculate it over a unit strip. Now, why do we calculate it over a unit strip? Because this is a one-way slab where 6 meter by 3 meter, if we get the ratio between the two, it's around 6 by 3 is 2. So we can treat it as a one-way beam, and we can calculate the maximum moments for the one-way beam condition. So we can take a beam of a unit width of 1 meter, uh, of a unit width, which is 1 meter, what we are taking here. Thereby, we are able to, we can calculate the total load, which is already the area load over acting over the slab per meter, and per meter into per meter. We can calculate that over a unit strip, over a UDL. So that would be 10 kilonewton per meter for 1 meter strip. Thereby, the moments mu L square by 8 is the moment per unit meter of the span. So that's 1.5 is the load factor into WU is 10 kilonewton per meter. We're calculating it over along the length of the slab. So this dictates the moment. This length dictates the moment of the slab, and it's calculated at the maximum would be at the center point. So that would be then transferred to the shorter direction. That moments will be transferred to the shorter direction in terms of the reactions that would be generated along the shorter direction. Thereby, this would be 10 into 6.3 L effective, LE is L effective along this direction. This is 6, then you have half of this and half of this support. So it's 6.3 square by 8 into 1.5, this being the load factor. So the total is 74.4 kilonewton per meter strip, of this strip, which about which we are calculating, assuming that there is a UDL load of how much? 10 kilonewton per meter over this 1 meter strip. Uh, Thereby, the moment that we're getting is 74.4 kilonewton per meter, which is the maximum moment at the center or along this direction. Shear force we do not need to calculate. So, so now this moment would decide the giving of the design of the main reinforcement or of the longitudinal reinforcement. Now that's done on the basis of the under reinforced design method, where MU is 0.87 FYASTD. This is from the code NX G IS 456. So for under reinforced design, because the thickness of the slab is quite less, there is a little amount of shear force, and there is little amount of chances of XU by D crossing XU max by D. Thereby, moment MU would be 74.4 into 10 raised power 6. This is 0.87 into Fy into AST into 158. Now, D is 158. It was 150, but we got the overall this around 192 then. Now we are providing 200, so it would be 8 more than this. That's then D would become 158. This is 1 minus AST into 500 divided by B being the breadth of the unit strip, that's 1000 mm, into D, that's 158 into 20. So AST we are getting as 1386 per mm square per meter of the strip. Now where are we providing this? This we are providing across the moments are determined about here, and we are providing the cross-sectional area of the bar cutting that moment about this direction to act as the main reinforcement. So the main reinforcement design is along the shorter direction here, and so the cross-section of the bars are actually resisting the moments of 74.4 10 raised power 6 Newton mm. Each bar, now if we are providing a 12 mm bar along this direction, so each bar would have a cross-sectional area of how much? 113.04. That's 3.14 divided by 4 into 12 square. So for the area of steel required 1386 per mm square per meter strip of that. So how many bars do we require? If we provide 12 mm bars, we would require 12.26 bars, and the spacing would be 1000 by, now 1000 is the width of that bar strip, of that strip. And we are requiring about, this is 12.26. So that's around, we are requiring around 81 mm spacing between the bars. That's quite less. So we want to increase the bar spacing. Uh, Thereby, we are providing 16 bars. So the area of the cross section of each bar then would be 200.96. Again, 3.14 divided by 4 into 16 square. So the spacing would then be 1000. That's the unit strip divided by 1386 cross 200.96 whole cross 200.96. So we're getting a spacing of around 145 So that's good. So the main bars we are providing is around 16 at the rate of 145 center to center. Next comes the distribution bars or the distribution reinforcement. Now the distribution reinforcement is provided along the longer direction. Now here in this case, the distribution reinforcement would be 0.12% into B cross D. So it's 0.12 into 1000. That's 1000 is the B, the unit strip along the longer direction. This is again from the code IS 456, where it's mentioned that the distribution reinforcement has to be 0.12% if it's a high deformed bar. So this is B and D is 200, or the overall depth of the beam or the slab that we have taken, divided by 100 because this is in percent. So we are getting 240 square per meter strip. Now per meter strip along this direction, per meter strip, you need to provide the distribution reinforcement. Now if I provide 10 bars as the distribution reinforcement, which is less than what we provided in as the main bars, which were 16 cross, the क्रॉस सेक्शनल एरिया ऑफ ईच बार नाउ द डिस्ट्रीब्यूशन बार विच वी आर प्रोवाइडिंग, जो हम 10 का प्रोवाइड कर रहे हैं, तो उसको वो डेट इज अराउंड 78.5 स्क्वायर. तो जो स्पेसिंग है बार्स की, दैट वुड बी 1000 because that's 1 meter strip. 1000 divided by 240. 240 is what? 240 is what we have got is the area of the distribution bar into 78.5, the cross-sectional area of this. So that's 327 But the maximum spacing that you can keep between the bars is 300 Remember that. And so we had to provide the 10 bars at 300 center to center. Now what you could do is you could reduce the bar dia further to 8 but it's not recommended to do that for slabs. You should at least provide 10 bars in slabs. And not go less than that, not to provide 8 bars, because they have certain more issues, and you don't get 8 bars mostly in the high deformed uh, in the market as well. So even if you get that in the high deformed, but still there are problems with the rib connections and the other things. So what we are doing is we are providing a 16 bar, 145 center to center as the main bar, and 10 bars at 300 center to center as distribution bars. There is one more thing that you need to focus on is the there is at the ends. What happens is that towards the ends, let me show this. This is towards the ends. What is happening is that there are supports here. For example, the support condition is somewhere here, and then you need to extend these. If this is the support within this red and the black line here, then you are actually extending the bars over the supports as well. And you need to provide the cover from the ends. So if this is 300 in total, the support, you need to provide a cover of 30 as required on the bottom face. Similarly, you need to provide a cover on the sides as well. Further, you can keep just in order to check for tensile requirements towards the ends. Although this is a simple support condition towards the ends, the edges are simply supported, but you still need to go for certain amount of tensile. What is happening is that there is a bar that is running somewhat like this towards the ends along the longer direction, for example, or in the shorter direction, whatever we take. There is a support on all the four edges. So there are supports here. So what is happening towards the ends is that although this is hogging, sagging moments that are being generated here in this case, but there is certain amount of negative moments being acting at the end here, somewhere here. Certain amount of negative moments acting here and here. So even in the case of simply supported, where the ends are prevented from uplifting, so the slope does not come out to be zero at the ends, it comes out to be a value greater than zero towards the end. So there is a certain amount of tensile uh, stresses developing towards the ends, and there could be a case of the torsion also developing. So further, because of all these things, there is a possibility, because the ends are supported, the tensile forces that are generated at the ends, there could be a case of a rigid support condition happening at the end, and that rigid support condition could lead to the development of shear forces. So what we do is that we provide uh, the ends are cranked up or bent up. The bars are bent up towards the end. So this is the slab, and the ends are cranked up somewhat like this or bent up, and this is the center portion. Then you would have this from point 1 to point 1.5 of total length L, uh, is this from the ends up till this point. You could start the cranking up or the bending up of the bars. Similarly, on this side, it will be 0.1 to 0.15 from the face of the support, or not from the face of the support, from the face of the column, sorry, of the slab. From the face of the slab, you are cranking it up at zero point 0.1 to 1.15 of L. L is the effective length here. So you can say it's LE. So that's the effective length. So thereby, now the requirement I just mentioned to you, the reason of cranking up of the bars is that there is a certain amount of tensile forces developing because of certain amount of fixity of the, even when it's simply supported, because it's prevented from uplifting. There could be another wall over it, there could be something else over it. So there is certain amount of fixity always in the slab. So thereby we are providing such a phenomena. So that's about this lecture. uh, Thank you.